Right.
Got it.
Okay.
All right. It's not Rutherford. I'm not going to start shouting through the other end of Kentucky. So hi. So now after we've talked about FANGs for most of the morning, and which has fantastic and wonderful data, I'm going to talk about the sort of a complementary exercise, which is what can you do if you actually have a background like this. You happen to have this configuration, right? You have a lot of astronomy depends on sheer dumb luck. This is part of it. If you just look at enough things and you find where you have two galaxies that happen to be there, it's just a little not dark enough to show you this, but so this is VV191. That was sort of the ideal overlapping pair. You've got an elliptical galaxy in the background. You've got a spiral galaxy in front. Some of the earliest JWST data in NIRCam images was taken on this for a early release science. So we all got to play with this. It was really a particular fun Zoom call where we all got to giggle about all the little background galaxies you can pick out, and you can sort of see that this elliptical galaxy has a lensing event, completely unrelated why we wanted to look at it, but cool, we'll take it. So the reason that I'm looking at it is this these structures here, which is the dusty foreground. So you can actually, if you use an elliptical galaxy as a light table. Light table is what you use to look at photonegatives. Photonegatives is pre-CCD in your camera. So feeling like this is very old school, but you can use it basically as a background light to backlight the dust itself. So you can learn about the dust that way. And the neat part is that you can now do it at the wavelength and especially at the resolution of Hubble and James Webb, and not have to force ALMA to do this because that's hard. So FANGs happens over here in the nice stellar disk, and the other part is that you can now go out to the overlapping galaxies. You can actually go as faint as you want because you're not constrained by the emission from that dust. Actually, you don't mind. You're actually backlighting it. So complementary technique to FANGs very much. And so I'll be comparing lots to FANGs. And so we had a bunch of papers by my graduate student, Clayton Robertson. He made a great map. So he started with the AV map. So this is the amount of light that's missing. Because if you go like, well, this is what the elliptical should look like. And ellipticals are very, 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 very dull. And so they're this exact same profile all throughout. So you can say like, this is the amount of light I'm missing. So you can actually get an AV map that way. So I don't have to rely on dust having a known reddening effect, right? This is what you usually do in astronomy. You go like, well, I see that my object is redder, so therefore it has this much dust in front of it. Because like, I don't have to make that assumption. In fact, I can go test that. And so with a bunch of filters, this was from our HST program, and then we got a bunch of filters from the JWST one. We tried it in UV, but it turns out ellipticals aren't great in UV, so never mind. But we would very, very much like to get more overlapping pairs using ultraviolet. So I'm going to advertise, hey, you should all support UVOT, one of the 34 missions being canceled by the presidential request second time round. But, NASA missions are hardy beasts, so we'll see if we can keep them going. But we would like the ultraviolet information as well, because Hubble is a Hubble ultraviolet telescope, but only if you force it to. So UVOT being a much better thing here. So here's Clayton. He made this AV map, and so the AV map to begin with, and like figure out what our signal to noise was. In fact, a very large part of his PhD was figuring out the noise propagation, like what's the error propagation if you're using a backlight. This is not usually how you do this in astronomy. And then make not just an RV map, but also a reddening map. And so everything that's bright red is sort of is a very red attenuation curve. But what's yellow here is essentially the Milky Way. And then you notice that it actually gets grayer. So as dust grains get bigger, and it's sort of in an extreme case, you can think of it as I put a whole bunch of lead cannonballs in space and they just block the light. And so I don't see any reddening at all. Or I can put an incredibly fine graphite dust throughout and then everything reddens, right? So this, whatever comes out of a smokestack. This is Kentucky. There's probably a smokestack nearby. Go look through what comes out of the top at the sun, and then it becomes redder. And so you can say like, well, this is what I see the Milky Way, but you actually can see that if you're in darker, denser parts, that you see in the optical, you see actually gray extinction. And it's like, oh, that's interesting. But we also had J. W. Steve, famously known for infrared. So if I now go to include the infrared in so I actually include all the information. I have an AV, so at V band, and then I do this J band, and then H, and then J and H. And so if I now do these extinction measurements and I take an attenuation curve through that, that is sort of goes as alpha, the amount of attenuation in magnitudes goes as the wavelength over minus alpha. And so what's the wavelength at all of these points? Now this, I would like to point out something that professors know and everybody else in the room who isn't gray-haired or lack of haired yet, sort of can only appreciate hopefully later, is this is what I wanted 10 years ago when I was thinking, wouldn't it be nice to measure this stuff with overlapping galaxies? What I want is a map that actually tells me how common is the Milky Way attenuation curve. Because ask any extragalactic astronomer, which one of how did you account for the dust? I use Calcetti's curve, or I use the Milky Way curve, and if they're feeling really frisky, they might go for the small Magellanic curve, and that's it, like end of list. But it's like, well, this is what I wanted to show you, right? Here is where you go, like, well, it's redder if you go into centers. It's mostly Milky Way, but actually at the edges, it gets a little green. It gets a little off Milky Way. So it really depends on where you are in a galaxy. If you're having a supernova go off, if you look at a star formation region, what kind of attenuation curve, what kind of reddening curve can you expect there? So I want to keep linking this back and forth, and I want to see if I can map the range of environments that you can get. By the way, fun fact, if you talk to atomic hydrogen astronomers, and I come from Groningen, so that's everybody there, they kind of keep talking about the pristine H1 disk, because you see 21 centimeter H1 disks, go all the way out. And now I can just slap this picture up and go like, what pristine H1 disk? There's dust everywhere. You're just going to have to deal. And so we sort of started looking at the morphology of this dust. And the neat part was that, like, okay, this looks like this is part of the spiral arm. We can see that it's part of the spiral arm. And there's sort of a spur, and this looks like the sort of faint edge of the actual disk. And so look at the different distributions, the probability functions really of AV and RV. And so that's what we have here. If you take the whole thing, you get sort of the black line. But if you look at the different regions, you realize that there's massive regional differences. So what I want to start doing, and so if you heard an earlier version of this talk, what can the occult do for you or similar, it will be like, well, okay, you're in an SC galaxy, you're this far out, you're in an arm. What is the probability that you hit a certain amount of extinction looks like? What's kind of reddening factor do you get? So we look at it does vary quite a bit, but they keep to these distributions pretty well. So we actually looked at the fits, and you get these attenuation curves at these different places. But we were a little worried about the fact that it was red when we included the near infrared, but it was gray when it was only optical. What's happening here? And part of that was simply in the optical, you have little subclouds, and especially if you do the same thing, where it's like you look at it closer, it's like, oh, it's turtles all the way down. It's all little filaments, and then more little filaments, and then more little filaments. So we didn't have neat little spherical dust clouds. We actually had even subpixel. You have some more structure. These pixels, the resolution that we're looking at, the foreground galaxy's at about almost 300 megaparsecs. We're looking at this at a resolution about 100 parsec, which in the age of FANGs sounds, a little lacking, but also our galaxy is way further away, so we're doing pretty well. And we're in the outskirts, right? So this is the other part. We're actually looking far, far out from the normal sort of the stellar disk. So what we think is actually, these things become transparent in the infrared. So they basically regain their attenuation curve that they didn't have because of the cloudlets basically became opaque to optical transmission. So we also just use more information. So that was Clayton's contribution, and he defended his PhD, and I think he was very happy because he grinned the whole time. So yay. That was done. He got a prize for it. That's wonderful. So there was one more idea that we had, which was, well, if I have this attenuation map, I can see all this detail, so I can do a power spectrum of the thing. So I can do a Fourier analysis of the image. Yes, there is a bit of noise over there, so I'll learn how to live with that. And so where's the PSF? And I see the two slopes, and it sort of goes into maybe this is a PSF effect. So I need to go look at that a little bit closer still. This is the reason that this is called in prep. And so we look at the large scales structure for this whole thing, and we look at the small scale structure. It's hard to actually have the dust peak out here. You have to subtract these two bright galaxies in order to have it pop out. But we also had other AV maps. We had a couple of these from over the years. And so we had power spectra for all of them, but because they're all at different distances, also with different HST instruments and with different filters, it was a bit of an catch-all. But we did get the large-scale slope. So we get the large-scale slopes in our black points, that's us. And then Bruce Elmgreen did a couple, he did one on the FANGs, some of the FANGs galaxies, the PH emission. He did one on M51. Francois Combs did M33. And then it's here somewhere. But there's another author that did this in these two pH features as well. So we're looking at the large scale structure, and I don't know, it's everywhere, but basically the pH in the FANGs data, you see it sitting between 2D turbulence and 3D turbulence. Is it mostly bulk motions in a disk, or is it actually moving vertically as well? As far as you can tell, for the larger scale stuff, it's mostly below the 2D turbulence. So it's all shear motions in a single plane. Except over here, because this guy's weird, because it's an interaction. And so if it's an interaction, you're actually now messing with the planar motions. And so they're over here. I don't know what's going on here, so we'll have to look at each of these individually closer. If you're looking at the small scale structure, we're actually much closer to 3D turbulence. So it's actually, you see the motions, the bulk motion, the effects of bulk motion vertically as well in 3 dimensions, except that, there's still a couple over here, the BB191, for example. So we're interested in the slopes for both as a function of mass, maybe specific star formation rate, see how that shakes out. And then there's that intercept point, which is sort of the typical scale where you go from in the ISM from disk to the turbulent motion. So see what kind of scale that happens at. I was really inspired by this Francois Combs paper from 2012. I was enthusiastically reading it, and then he goes, "Oh yeah, and in M33 is the only place you can do this with Herschel, because that's the only one that's close enough to resolve this." So these are literally all the Herschel bands that we ever had a power spectrum for. But now I can compare this, and I don't even have to have the dust heat up. I don't have to know about the dust temperature. I don't have to know too much about the dust composition. I just need to know it's there. And so dust reliably extinct, so I can see whether and this relates to the column density. So I'm curious where this transition point sits every time. And then I want to compare that to the Milky Way. Again, thank you all for all the phenomenal FANGs talks this morning, because, basically you can point I'm going to do the same thing. I'm going to look at the attenuation maps from Gaia, from a couple others. And you get the small scale dust structure. So I can actually compare those slope, the power spectra from that to the ones that I'm seeing in the overlapping galaxy pairs. Of course, you can only do this with HST resolution. And for the longest time, it was just a bit of a fight to convince the HST TAC to get overlapping pairs, even though they're very pretty, I think. But we're going to be in luck soon, because we'll have Roman. And so Roman will give us basically all the nearby galaxy overlapping pairs. And fortunately, they start into the infrared. So I'm like, all right, that's a good baseline. Now give me the optical. So if you happen to find yourself on the Hubble cycle 34 TAC, please give me U, B, V, and I imaging on these things. Because, hey, this is what happens if you pay attention to talks. You can actually crop somebody else's slide real quick. And so, yeah, basically do the exact same thing. Look at these scales, right? So where here you worry about, is everything emitting at the same temperature? We can now, and then compare with the dust maps, which comes from AV, from attenuation. I can just directly compare it to that, but I can also compare it to the FANGS results, right? Notice that the other points were all from FANGS. They were all PHs. But I've asked for the last 15 years since Spitzer was a program, hey, PEH emission, is that a star formation tracer or an ISM density? And the answer has always been yes. So I would like something that is just an ISM density tracer, which I've got here, and then I can compare that to the morphology that I'm seeing. Do you see the same thing? So yeah, that's where I'm going to go with. Since this is your logo now, so it's I'll have to use that. So the outstanding issues, I kind of want to do still one sanity check. Did I get the wave number, pixel parsec, everything everywhere correct compared to the Milky Way Gaia maps? Comparison to theoretical expectations, I've got a couple of dust maps from various simulations. So do I see the same thing? Finish the write-up, which we STEM people love writing. Just fine, put words, one word after the next. And then add all the Pearl's friends that have didn't respond to my email. Get everybody on there. And the conclusions are, so low mass galaxies seem to have mostly 3D turbulence. This is something that we suspected already from various dust morphologies. They don't, if you see them edge on, for example, they are much puffier than they are if you take Milky Way types, like it's just a thin stripe. And so high mass galaxies are basically 2D sheets. Okay, that's not new to anybody who studies big Milky Way kind of galaxies, but we mostly base that conclusion on NGC 891, so it's nice to do it on more than one galaxy. The exceptions seem to be interactions. Okay, that's fine. You get to mess with the galaxy at that point. And so let's see how that matches up to the other ISM tracers. I'm not trying to outdo or compete with the FANGs. That would be silliness, but it was more of a, hey, I'm very curious how this matches to what you're seeing. How does what you're seeing in the center of a disk compare to the outskirts, for example? I'm very interested in outskirts of galaxies, little bits of star formation. Is gas trickling in there? How is that coming in? And so how do the local conditions compare to, like, let's say, the inner parts where we have much more pressure, much more energetic feedback? So inside, outside kind of deal. Nice and complementary. So we'll see. I have about, how many overlapping pairs do we now have, Trevor?
In total, or like ones that we can use?
In total.
Like 3,200-ish?
Okay, so over 3,000 overlapping pairs.
Wow.
Of various configurations and distances and whatever, and that's his problem now. But but it is we have a sample that we can start constructing, not just from very nice single examples, but actually start doing a holistic compare all of the overlapping pairs, the AV maps together. So. Since I'm also sharing this session, I hope that I stay within a reasonable amount of time. I'm a bit of time blind when I'm giving a talk. So, and if anybody wants to hit me up with a question, there's my email and everything. So thank you very much, and I'll take questions for a second. Because I realized it was a little bit over time. Sorry. I can take a question while he's. Yes.
Is your background galaxy bright enough so that you can observe this CGM of the galaxy in front?
The link with CGM is another great one. So we're sort of mostly thinking the disk and sort of thinking in disk terms, but especially if you start thinking edge-on galaxies, we have a bunch of edge-on galaxies that are backlit. You can actually see the vertical distribution as well. So you can see how much, how far is dust being flung out by feedback, for example. So that's another project I would love to do in my copious free time. And the other thing you can do is sort of look further and further out, but you can get a zero result, for example. So you can say like, yeah, there's no extinction here, but it gets harder to, the smaller the amount of extinction is to reliably measure it. It's possible, yes. Thank you very much.
And you shared the screen, right?
Yes, it should be shared. All right, so my talk's kind of a follow-up to Dr. Horta's talk. So I'm doing a overlap zoo. It's similar to Galaxy Zoo. If you guys never, I mean, I assume you guys have seen Galaxy Zoo, but it's for overlaps. So we need to find more of these pairs. And this is what the whole point of this project is. We'll get more to my motivation in a second. But first, I want to start with some of the background of what overlapping galaxies are, which Howard went over with a little bit. But I'll start with that. So here are some pairs that we have for occulting galaxy pairs. It's a little hard to see on the actual PowerPoint here, but you can also see on the back of my laptop I have one as well. But yeah, here on the left we have AGC 3314, which is found by Dr. Keel, who is also someone who works with overlapping galaxies, but he's retired now, so he still works on them, but not too much when he has free time. And this is VV191, which is also discovered by Keel and Dr. Howard and Clayton worked on. But yeah, overlapping galaxies, essentially there's a foreground galaxy and there's a background galaxy, and they overlap each other. And the background galaxy acts as a light source or a light table, like Dr. Howard said, and lights up the outer edges of the galaxy, or in this case, it lights up the whole galaxy pretty much. And so I will get into Clayton's presentations, or Clayton's figures and stuff as well. But for those who don't know what dust attenuation is and don't actually work with dust and stuff, so dust attenuation is basically the net amount of light lost from like when the light goes through the dust, from absorption and scattering. This also influences many of our measurements, so like star formation rates, also our SED modeling and our distances. So we had to correct for this, so it's important to know this information about dust attenuation. So we do this using something called the Coulting technique. This was discovered by Keel and White in 1992. Howard kind of glossed over it a little bit, but essentially you model both of the lights from both of the galaxies, and you subtract that light and you get your attenuation from that. We do this in two ways. We can do a rotational subtraction, so we could have these two galaxies and we rotate them and do the subtraction there, or we can model them using isophotes, so you can model both the galaxies. And I'm doing it with a foreground spiral galaxy and a background elliptical galaxies. The best way to do it, but you can also do it with other pairs as well. But here are the maps from that Dr. Howard showed for Clayton. So this is VV191. So I'm going to kind of gloss through these a little bit. If you guys want to check out Clayton's paper, it's already published. And then here's the other maps that Dr. Howard also showed. Yeah, this is something we can do that we hope to do for more pairs, and that leads me to the motivation of my project. So these overlaps are really rare and they're not often cataloged. So a lot of these overlaps are found like in Galaxy Zoo. They have like an actual question for overlaps, but nobody really does anything with them. And it's only really me and Dr. Howard, I guess now, that actually does anything with these. But at the time of before my work, 2,400 pairs were actually identified manually, most of them manually identified through Galaxy Zoo. Also, our other catalogs are getting bigger and bigger, so we get more and more data, so we can probably find more and more occulting pairs in those. Zoobot, which is with Galaxy Zoo, can't actually catalog these pairs or can't classify these pairs. It's not fully reliable yet. I think there's work being done to fix that, but I'm not too sure about that. You'd have to ask Dr. Walmsley about that. And also, previous studies lack these ellipse-based annotations for these galaxies. So to actually do this rotational and isophotal fitting, we need ellipses fit on the galaxies. And so a lot of these studies didn't have that as well. So the solution for this was to do a citizen science approach with human volunteers to actually classify and annotate these galaxies. And so that's what my whole project is. You guys may have seen this last year when I did a poster on this, but this is the full, I actually finished it and everything is published. But this is all my motivations for this project. And this leads me to my main goals. So my main goal for the project was to design a new workflow to classify these pairs because one has not been made before. I wanted to actually host the project on some platform. And also wanted to classify these according to Gill's classifications that he pioneered for these occulting galaxy pairs for use in dust attenuation studies. And then on the right here is like a little logo I made. It may be changed in the future, but it's something I made. So for my sample selection, I used Galaxy Zoo decals, which is from Galaxy Zoo. I did votes above like overlap. So there's actually overlapping question here, which I mentioned earlier. This overlapping question gets a certain amount of votes and a certain amount of voting fractions. And I did basically a cut on that for votes above 13 and voting fractions above 0.28. And that gave me about 2,400 candidate pairs. Now these pairs are not all overlapping galaxy pairs. Some of these may be interacting pairs. That's one of the limitations with my project, which I will discuss later as well. So to actually get the images for the project, I used DESI Legacy Survey, so DR10, which is I think the latest release that they have. And I took these cutouts using a Python module called Legacy Stamps. This essentially it goes through the Legacy Survey and grants you just an image of the galaxy. And then I scaled it using Nyquist interpolation, which is a really old paper from Nyquist there. And so my classification workflow, so I did this on Zooniverse. So again, a lot of you guys may have heard of Zooniverse with Galaxy Zoo and stuff. So I included about all my images on in the workflow, and I retired each of these images after 4 classifications. Now, people might see some issues with that, and there were some issues with that later that I'll discuss. But overall, we got about 9,500 classifications, so votes in total. A total of 62 people actually participated in this. 15 were registered people, so most of the people that actually participated in the project were in our research group. And so they did most of the work, so 96% of the classifications, and 40% were unregistered, so I sent it to family and friends, and about 4% of the classifications for that. So for my actual workflow, so I did a decision tree similar to actual Galaxy Zoo projects. This decision tree is highly flawed, I will say. I've actually worked on a new one that I believe will be a lot better. And this decision tree also assumes that there's nothing known about the actual pair itself. Essentially I started with what type of the galaxy overlap it is. So we have different types. So spiral overlaps, spiral elliptical overlaps, elliptical overlaps, or other pairs, or other like emerging or interacting, or you can't actually tell what it is. Then I went through like which can you distinguish in the foreground, which disk can be viewed nearly edge on. Is the disk completely edge on? Which galaxy is bigger in size? Is the background galaxy significantly smaller? And then I also had the annotations as well, and also what the degree of overlap is as well. So these are the questions I showed to the volunteers, and this is what they used to classify. Again, I will discuss some of the limitations with this later. So after I got the classifications, I did data reduction. So I had to export the data from Zooniverse. I had to clean up the data and produce tables. I had to break some ties. So as I mentioned, the 4 retirement classifications was actually led to ties. So if I had 5, like an odd number, it's a even number, I wouldn't have as many ties. But we were limited in time, so we only could take so many classifications for each actual galaxy. So I did that. I did some updating to actually fix those ties, and then I produced a final classification. And I also categorized each of these pairs based on Keel's work. And this leads me to my actual catalog, which I will be discussing the morphological catalog. There are other parts with like standard Galaxy Zoo and votes and all that, but I'm not going to discuss that in this presentation. So here's my catalog. So I have on the left here is a table with the different pair types that were described by Dr. Keel in his 2013 paper. So we have F types, which are face-on spirals with and a background elliptical. This is VV191, pretty much. Then you have Q types, which are background galaxies edge-on and radial. You have phi types, which are foreground disk-on, disk edge-on, and background elliptical galaxy. You have an X type, which are basically just 2 edge-on galaxies. SC is spiral elliptical pairs that are not listed in the table. S is 2 spirals. B is a background galaxy is very small. E is 2 ellipticals, and this delta Z is just to check if they're merging or not. And we had about 131 of those that aren't actually show any interaction. So this is above a redshift of a delta Z of 0.008, I believe. And then the last one, CT, is just they couldn't tell which is from the foreground or background. It's about 89 of those. So out of the 2,400 in our sample, we got about 765 that were identified. 189 of these were in the Keel's catalog. So we have about 576 new pairs that we found. So that's great. We'll be able to find more in the future as well. Again, 131 are not interaction emerging, and about, I can't really see it there, but it says about 1,500 were classified as other. So these are galaxies that were either interacting or they were actually a star overlap instead of actual galaxy overlap, or were they couldn't tell which the galaxy was, or overlap was in the category. So here's some close-up pictures of the overlaps. It's a little hard to see resolution-wise from these projectors, but you can see many of the pairs we have. I'm just going to go through these a little bit because I might be. Some of these are some of the beautiful pairs right here. This one was in Keel's catalog as well. I really like this one as well. And here's our last part of the image there. So for the catalog, I also got different measurements as well. So I have SDSSEs, DESI-IDs, the R-band magnitudes, and then the redshifts as well. So I did this using my own method of basically I queried the galaxy and I if the redshift was close enough to the center of the galaxy, I took that as the redshift using the user provided annotations that we had. I actually manually verified all of these, manually verified all of the actual automation that I did. It was about 98 to 99% effective. So there's some pairs that were misidentified redshifts, so they took the redshift from the other pair. But I fixed those manually. So about 22 of these pairs did like the center pairs didn't have redshift measurements, and about 403 like off-center pairs did not have redshift measurements in SCSS or DESI. So majority of these are ellipticals because those are hard to get with redshift measurements in the fibers. So I did also do a classification accuracy test. So the first test I did was with magnitudes. So if you have a dimmer foreground galaxy, it was found that you actually have it's harder to identify which galaxy was in the foreground or background. But if it was a brighter foreground galaxy, you could easily tell which was in the foreground or background. This is visually, again, I didn't mention this, but classifiers didn't actually have access to redshift measurements like I did or Kill did. So they just did it purely based off the images. So this was a good metric I could show that actually tells how well they can identify the actual galaxy. And then the second part I did for redshift difference, so how separated are these galaxies? So if they're closer together, is it harder to tell? Or if they're farther apart, is it easier to tell? So the bulk of my data is actually in this region. So everything here is pretty well constrained. Everything past this point is kind of hard to, there's low sample size, so I wouldn't trust the right side too much. But in the bulk of the data, we can that it's the larger delta Z, it begins to become easier to identify which galaxy is in the foreground and which galaxy is not. I also compared it to Dr. Kill's catalog. Out of the 189 that were actually overlapping with his catalog, we had about 49 that actually agreed with his catalog. So this seems like a really low number of agreement. But I believe this difference is because the survey quality and he actually had access to redshifts. So that could explain different classifications. And I tried to provide an example here, but it's a little hard to see, but you can see SCSS in comparison with DESI, it's like SCSS, it's like a blob. Okay, and then DESI, it's really easy to see the features as well. I also compared this with the Galaxy Zoo. This is from my paper. And so basically you can see that a lot of this is a percentage of agreement. You can see that there's some good agreement if you took the raw redshifts, but if you take the debiased redshifts, there's some disagreement there. If you have a question about that, just ask me. So I want to address some limitations. So the first problem was the requirement for classifications is too little. The solution again is to do another iteration of this and do a public release so we can get more classifications for these pairs. There's also ellipticals. I can't tell with my decision tree, couldn't have annotations. I adjusted the decision tree to fix that. Other classifications, the classification was too broad. I think so. I was going to add subtypes to that as well to reduce and remove the subjective questions. And spirals can in the decision tree used for this one could accidentally be voted for spiral ellipticals or having an elliptical galaxy in them. But since it was an internal classification project, it didn't happen. But it would be probably an issue in a public project. So that I'd rework decision tree again. And then my selection methodology could be improved a bit. There was a lot of false star overlaps, and so this could be an interaction. So this can be improved as well. And that leads me to my conclusions. So we basically developed a new classification workflow for classifying these occulting pairs. So we got about 600 new ones and about 200 ones that were actually already found. Our approach could benefit from additional refinement, and a public release of this overlap zoo is essential because we're getting more data as time goes on. And I believe actually Galaxy Zoo Ruben should be. Yeah, if you guys want to check out my paper, I put the QR code there. If you want to check out the panel, just the QR code for that. Take any questions?
Any reason as to why you have the number 13 for boats? Or greater than 13?
Greater than 13 or less than 13. I don't know if I have the slide on here actually. It was just try to get as many pairs as we can, because the actual the selection for like the votes and vote fractions, there was a bunch of pairs like in like the bottom left of like a plot. There was like a lot of pairs there. But we wanted to do like a modest selection so we get a lot of overlapping pairs that we can get, but we also get biased by some of the star overlaps pretty much. Yeah.
Any other questions? Who's the next speaker?
It's me.
Okay, great. Thank you so much. Trevor. Yeah.
Are you on the Zoom call? You share your screen, right?
Yeah, that's my screen. Can everyone hear me online?
It's showing you as talking, so
All right.
you're good. Yeah.
For sure.
Mhm.
All right, well, thank you everyone for bearing with me while I figured out how to set up the Zoom and all that. And for inviting me, letting me contribute a talk today about some of my research that I'm currently doing at the University of Cincinnati. I'm a graduate student there, but hopefully in a month or two I'll be graduated and be officially a doctor. So it'll be cool. This is one of my thesis projects, which is one of many things that I worked on. And it's about the peculiar motions of BCGs in the South Pole Telescope cluster cores. So, as we have heard during this weekend, we are astronomers of many different backgrounds. So, we give a little bit of background about the actual problem we are trying to solve here. So, the universe is predictably structured into a web-like structure of filaments, and at the intersection points of these filaments are nodes in which inflows of matter become dense enough where we're able to form more massive virialized structures, such as galaxy clusters. These clusters form through a process of hierarchical mergers that is dominated by dark matter halo structures, where formerly separate systems combined to form more modern galaxy clusters. The dark matter halo is the component that is dark matter dominated that dictates the cluster's shape, centroid, and gravitational potential. Through this hierarchical processes of mergers, the galactic components also experience, extreme astrophysical processes. Specifically, the brightest cluster galaxy, which resides at this center of the antisense and also the modern structure, has a formation history intimately tied with the formation history of the cluster at large, and as such should share some similar properties between the cluster itself and the BCG. Specifically relevant to our project is that we expect that the brightest cluster galaxy should reside at the center of the cluster at rest. And the reason this is interesting is because when you actually make this measurement on a statistical sample of galaxy clusters, you're able to measure the characteristic offset and determine whether or not that can be attributed to measurement uncertainty or if it is an actual signature. If it's an actual signature, you can come up with that explanation either within the context of astrophysical processes that we know affect galaxy clusters, or by applying some more exotic form of dark matter to see if it matches the distribution you observe. And this has been done in form of simulation work. Here you can see how different interaction cross sections of self-interacting dark matter lead to larger tails in the distribution of observed offsets. So that last slide, I kind of talked about the what we're investigating and the why it is interesting, but now we're going to go into the like how we can actually do that. There are two methods to test, this kind of idea of like BCG centrality, which I'm going to be calling the central galaxy paradigm or CGP. And one way is to test whether or not the BCG is in motion with respect to the cosmic recession of the cluster, which we will characterize as the BCG peculiar velocity, is how much it's moving relative to the cluster and the cluster's frame of reference. And then the other way is to test the offset of the BCG's centroid with respect to some proxy to the centroid of the cluster, whether that be lensing or the X-ray peak or something else. And former studies have done both of these tests before, but a lot of them are either statistics limited or redshift limited. For instance, here, this is a relatively small cluster sample from the Donahue paper for the frontier fields, and then this, or the clash, not the frontier fields, my bad, the clash sample. And this is for a bunch of Abel clusters, which are very low redshift, measuring the peculiar velocities. So what we want to do is apply this to statistically cosmologically complete sample, which the South Pole Telescope provides us. When we opt to use the peculiar velocity of the BCG as opposed to the centroid offset, because one, this measurement has never been done at high redshift, and also we're able to constrain this measurement a lot better than we are able to constrain the centroid of the SPT clusters, which are mainly determined by the Samuel-Zeldovich effect, which is a little bit hard to estimate the exact center, which you'll see in a slide later. But by requirement, we need spectroscopic information to actually do this measurement, to measure the peculiar velocity of the BCG with respect to the cluster in a sufficient sample, in a sample of clusters with sufficient spectroscopic data that we're able to accurately characterize the motion of the cluster and its redshift. And we apply a cut of at least 15 spectroscopically confirmed cluster members to actually make this measurement on. And, kind of in this regard, I said, one way we can explain away if we observe the signature is actual astrophysical phenomena. So what we want to do is, for the subset of clusters we're able to do this, actually characterize the dynamical activity in that cluster. And we do that using Chandra X-ray data to make measurements of the intercluster medium, which is a common practice to actually measure the dynamical activity in galaxy clusters. And first, sufficiently large subsample of our subsample, we have Chandra X-ray data, and we're actually able to make these measurements. I'll also briefly mention that BCG selection is a factor. It's not always so cut and dry in high Z clusters when you're using shallow ground-based data, what exactly the brightest cluster galaxy is. So we use this automated algorithm developed by some collaborators in combination with information about the lensing arcs when they're present, the X-ray peaks when we have the X-ray data, and a bi-eye inspection of all this information to get the best estimate of what the BCG actually is in our systems. Okay. So as I mentioned, we're measuring both the normalized BCG peculiar velocity, as well as the dynamical state, which we use this combined parameter M, which measures morphological properties of the ICM throughout the whole of the ICM, looking for substructure, and also metrics sensitive to the core properties of the ICM, which probe whether or not a cool core has formed. And what we find is that when comparing these two measures, they don't seem to have a direct correlation. But we do see on the left end of this first plot here that there seems to be a specific increase in BCG peculiar velocity for the most disturbed objects. And we kind of apply a cut from this visual inspection, rejecting objects greater than n equals negative 1.5 to try to remove these objects and do a test on the whole sample as well as excluding the most disturbed objects to see if some of these effects that we're going to talk about in the next couple of slides apply to the whole cluster sample or just objects that should be following the CGP. We also exclude 3 clusters without Chandra data, which you can see here. We use the offset between the SC position and the BCG as a metric to try to measure the dynamical activity of objects without X-ray data. But as you can see, this is a very noisy metric with the error bars. So we don't actually use it to cut out objects. Instead, we just apply this cut, assuming that objects with, a normalized BCG peculiar velocity magnitude greater than 0.75 are disturbed. And we can see that these two subsets of clusters are distinctly different, even when accounting for sample variance, which for the relatively small most disturbed clusters is quite large. Okay. And now the actual test that we do. So, like I said, we want to observe a signature beyond what can be accounted for measurement uncertainty. And one thing we can assume is that each observation is just a realization of a normal distribution where the individual normal distribution's standard deviation is equal to the measurement uncertainty. And we combine these into a single parent distribution to describe the situation for a whole cluster sample. And then we can also take the absolute value of that distribution to get a description of the magnitudes of these offsets. And what we do is we compare our observed distribution to this, parent distribution described in the case where the true BCG peculiar velocities are 0 and the observed offsets are just due to measurement uncertainty. And what we do is we assume that the observed distribution, the theoretical distribution is greater than the observed distribution, and we reject that hypothesis with a p-value of 2.3 times 10 to the negative 6, which is high statistical significance. And we get a median offset of about 0.24. So this is good. We observe this signature is real. It's truly happening, at least for the whole 85 cluster sample. And we apply it again to the subsample, removing the most disturbed objects. And what we get is that, obviously the values decrease mildly. The average goes down to 0.23, and the p-value decreases to 2.97 times 10 to the negative 4. But this is still a statistically significant measurement, and I think you can see that from the visualization and the CDF. These gray lines are also just realizations of the parent distribution for equal to 4 sigma. So it is beyond what can be accounted for measurement uncertainty alone. Okay, 1 minute. Okay. Then, so I was just told that 1 minute. It's a slide, anyways, that says that there's no real correlation with mass or redshift, which is slightly against theoretical predictions because we assume that for a fixed redshift, more massive objects should have higher peculiar velocities and dynamical disturbance, and for fixed mass, lower redshift objects should have lower peculiar velocities and be more relaxed. But in the literature, this has been debated anyways, and if there is a correlation, it seems to only be for those most disturbed objects. And I'll just throw out my conclusions here because I know I'm out of time. Yeah.
Questions?
What do you think is the reason for the shift that's actually observed?
So a couple of studies have like I showed one at the beginning, like investigated this idea of like self-interacting dark matter as an explanation, which could be true. Another explanation could be that Adrian feedback is somehow disrupting the profile and making it more chord in the center. The like actual explanation is that there's clearly the potential isn't sinking in as much and locking down the BCG as tightly as we would expect. The physics behind why that's happening is hard to constrain. I'm not gonna state an answer as to which one it is, but yeah.
Could you say again, what was the highest redshift that you've got in your sample?
Let's see. It's looking like 1.15, let's say.
Okay.
Yeah, it's written in my paper somewhere the exact number. The median redshift I do know off the top of my head is 0.93.
All right.
I have a question. So, are you this only works if the BCG basically is completely virialized, and so the cluster is also completely virialized. Did I understand it correctly?
So I was just saying that clusters are they're structures that are gravitationally holding themselves together, right? But I'm not saying that they're dynamically relaxed such that we're not assuming hydrostatic equilibrium, if that's what your question is.
Yeah, because the BCG sort of yes in the center, but maybe it's still sloshing about.
Yes, exactly. Yeah, and what we're trying to do is people have been this kind of built off that original idea of this sloshing happening, but a lot of people haven't really been characterizing how much beyond just measurement uncertainty you're doing. And then in the paper we also deconvolve with our measurement uncertainty to get something that can be comparable to simulations. The simulation work needs to be developed though, because they haven't done much of this measurement, and it was very mass limited, which makes sense because it's hard to simulate clusters.
Questions? All right. Thank you very much. I think slipping slides are.
Just stream it. Just share your screen on Zoom.
No, I need the type plugin.
I got one here.
Oh, I haven't.
But if you're on the Zoom call, you don't need to connect.
That's right.
But to show the screen, right?
No,
Oh, gosh.
no. If you're on the Zoom call, no, you just
Yeah, share your screen.
you're sharing the screen.
We've just been plugging in for Bacchus then. Okay.
Yeah, basically. Sorry.
I thought it was going so smoothly, the screen's going up. Usually there's a 15-minute pause as you try.
Yeah. That's why I usually like to have it on the podium computer, because then you can just easily switch the talks.
But then you've got Tim writing his talk 5 minutes beforehand, so he can't hear me, so I'm good.
You're also doing
Yay.
Okay. Good afternoon, everyone. My name is Shikha Pandey. I am a second-year PhD student at University of Louisville, and I work with Dr. Benny Halveda and his research group. Today, I'll be talking about star formation histories from a stochastic point of view. So to begin with, let's consider two very different types of galaxies. We have these massive systems like Milky Way, spiral galaxies, and we have dwarf galaxies. Spiral galaxies are these structures that have very well organized star formation. So when you observe the star formation history of this galaxy, you see a smooth, predictable, smooth curve of the star formation history. So that tells us that star formation of massive galaxies are relatively stable over long periods, which is not seen in dwarf galaxies. So we're going to take a look at why this variability is observed in star formation using observational data. So starting off with, we have this plot from Maddow and Dickinson 2014, which plots the star formation rate density as a function of redshift. So as you can see here, the redshift peaked at, the star formation peaked at around redshift 2, which is about 10 billion years ago and has been on a decline ever since. When we try to zoom in and look at shorter timescales, for dwarf galaxies at a timescale of about 200 million years, we see a lot of variability here, where there's a burst of star formation somewhere here, and then it drops and has been dropping ever since. And for Milky Way, it's not as obvious here, and the timescale is about 1,000 million years. So there's less variability seen in massive galaxies. So stochastic star formation is basically this idea that galaxies do not just form stars at a smooth rate, but instead go through these violent burst and quiet coasting phases. To understand this behavior of galaxies, we need to know what's going on in it, right? So we as Faith covered, that galaxies have molecular gas clouds collapse, gas cooling, supernova going off, H-chain feedback, all kinds of winds, stellar winds, galactic winds, etc. And these processes range from a few million years to a few hundred million years to a few billion years, which we will not talk about because mergers and quenching. So talking about timescales, we have this very beautiful, it's not a plot, but I like to call it a plot because of the x-axis here. So we have timescales at which there are these shorter timescale events where it's a supernova, gas cooling, something that happens over a few million years. There is this part here, which we use to study star formation histories of galaxies, which basically focuses on galactic winds, stellar winds, etc. And the pink part here, which is quenching and mergers, which let's just ignore that for now. So how do we constrain this observationally? So we have tracers or clocks, as I like to call them. We have ultraviolet continuum that is emitted from hot O and B type stars, which traces a star formation rate of up to 100 million years. And we have H-alpha recombination line with a wavelength of about 6,563 angstrom. These emission lines can be seen around gases, around these hot O and B type stars, which traces shorter timescales of about 10 million years. So the spectroscopic data is coming in from the Anglo-Australian telescope, which I don't need to tell you all where it is. It's a 3.9 meter telescope. It has a 2-degree field positioner, which can observe up to about 400 fibers. 392 of these can be galaxies. And it has AA omega, which uses this 2-degree field fiber to give us spectra. Great. AAT has observed the Laduma field looking at distant universe with the Meerkat array. Laduma field is in the Chandra Deep Field South. So a little more about AAT here. It catches up to, it has about 400 fibers here, has 30 sky spectra right now with the data that we have, 8 standard stars for flux calibration, and about 356 object spectra, that is galaxies. I've done redshift measurements, and the redshift of our spectra is goes up to 0.35. So this is all just, this one fiber is just one spectra, and there are about 356 object spectra in one fit span. So that's about 10,000 spectra that we're going to look at right now. So coming to spectroscopic analysis, the wavelength range is 3,800 to 8,800 angstrom approximately. And this is needed because we need the 6,600 6x63 angstrom nanometer scales for H alpha strength measurements, right? So to get the star formation rate estimates, we go through all these processes that should not be covered in one slide, but we have flux calibration, continuum subtraction, redshift measurements, signal to noise ratio, dust correction, and aperture correction. Probably the most important part of this. And once we have the luminosities through spectra, we're going to use this famous relation from Kennicott 1998 to get star formation rate estimates. I have this line here, you'll notice it's the line measuring library, which will basically measure the strength of my H alpha emission line. And I just like the fit here that's doing because that is exactly what we'll be doing. So I've just added it here. And that is the H alpha, which is of course redshifted, but that's the H alpha strength that we're going to look at right now. So great, we're going to get H alpha estimates, star formation rate estimates from the H alpha emission line. Okay, what about the UV data? To get star formation rates from UV, we use spectral energy distribution modeling, which is great because Kyle from our research group is working on it. So I cannot worry about this as much. But Bagpipes is the modeling that we're using, and it takes input parameters for luminosity, dust, and IMF, and then spits out the cosmic star formation history and star formation rate of the galaxy. So once we have both of these estimates, we're going to define our burstiness indicator by taking a ratio of these two timescales. So shorter timescales over longer timescales, and we're going to see if the galaxy has had a burst of star formation or has been, we see a decline in the star formation. So if the ratio is greater than 1, which means the numerator has higher contribution, which is H alpha emission, so the star has undergone a burst, a recent burst, whereas if the ratio is less than 1, there's greater UV contribution, which means declining star formation. And if the ratio is 1, we see a scatter around this, I call it main sequence, but it's really misleading. But this is what we see here, that there's a plot for this, there's a line for this ratio equals to 1, which just shows a steady, stable star formation. So quantifying stochasticity as a function of different parameters like mass, gas supply can tell us a lot more about the galaxy and the physical processes that we're trying to look into going back. So SSFR, that's specific star formation rate, as a function of stellar mass, just represents growth efficiency of a galaxy. In these plots here, these are simulation results. You'll see that the top panel is for lower mass galaxies and the bottom panel is for higher mass galaxies. There is more scatter here in the lower mass galaxies as compared to higher mass galaxies. These black dotted lines just represent look-back times at a difference of about 200 million years. And at all redshifts, especially at higher redshifts, higher mass galaxies have lower specific star formation rates. So we can look into that, and it's kind of an interesting result to look into based off of the data that we have right now. So as just summarize what we're looking into, while the universe as a whole might form stars at a nice smooth rate, individual galaxies operate in chaotic bursts and violent cycles, bursts and coast cycles. The two-clock approach effectively isolates these bursting and coasting phases of galaxies, which help us constrain very recent star formation. Once stochasticity is quantified, we can link it to steady gas supply in galaxy, its stellar mass, and the galactic environment. Thank you.
Good stuff.
Yeah, super nice talk. I'm wondering if you could say a bit more about your dust correction, because the two tracers you're using are.
I just added this backup slide today. So for dust extinction correction, we'll be using Barmer recombination lines, so H alpha, H beta ratio.
Yeah.
Once we have flux measurements. So right now I'm stuck at flux calibration because I need to convert it from pixel units to flux units. So that is what I'm doing right now.
Any other questions? The dust correction for UV is Kyle's problem.
Uh-huh.
I guess just quick follow-up is like, do you see equal number of detection in H alpha and H beta? 'Cause
Yes, so I just briefly plotted all the spectra that we have in just one FITS file, and I was able to observe like 15 to 16 H alpha strength emission lines, which is decent considering it's from the first file itself.
Right.
And I have more files to look into.
So it's not like your sensitivity is dropping fast to the blue end, because usually sometimes when we look at optical data, the blue side the sensitivity is not as good as the red side.
Not right now, and hopefully not later, but yeah.
That's been done before with this kind of data, but
Yeah.
I'm not sure if we got it to the same depth, so let's see. There's more spectra coming. We'll talk about all the Roman and all the cool imaging that's coming, but foremost is on the telescope, and it's going to eat everybody's lunch because it's very fast at getting spectra. So that's your next problem. The lack of spectra is not the problem. So yeah. Thanks. Thank you.
Thank you.
Shorter copy though.
Yeah.
Yeah,
Short
last
copy,
call for comment.
If you have a poster, if you don't mind going ahead and taking it down during this break. And then Krista, can you give instructions on how to get to the planetarium?
Yeah, you can bring food up to the planetarium as long as you don't spill. So, go up to the 4th floor and it's in this corner. I'll have the door open.